Hello folks, well Cadbury's would want us to say thank Crunchy it's Friday. Got a different Norwich tie on today and the old cufflinks are back in force, so it's time to have a little bit of fun. We're going to start off by looking at the railway tracks and see how everyone got on with that. Well, see how I got on with it. I don't know how you got on with it. Right, so here's my solution, and if you check everywhere we should be right. I have double checked on it. Now it's one of those things that sometimes I can do this without using pencil at all, but sometimes when they're a bit trickier, that's what I like to do. Otherwise you could be standing there or sitting there and your brain's working really hard and you're trying to work out what's going on. You can see here that I used a bit of pencil to experiment as I was going along until I was sure. One other tip that I'll share with you is when you're thinking about counting the number of squares that the tracks are going to be going through, when you get to really hit the high numbers of 6s and 7s, I tend to just think about it's going to be every square's got track apart from 1, and on 6 there's just going to be 2 gaps. So for example, I'd worked out that I had to get from there to there like that, so I knew there was a gap there, so I knew there was only going to be one more bit of gap that we had there, but this is the bit I found the trickiest. Anyway, there you go. It's time for us to move on now to the great world of similar areas and volumes. Right, now most of today's thing is going to be about working through some practice GCSE sort of problems, but before we do, I want you to have some understanding of why we're going to do the process we're going to do, because if you understand it, the process itself is quite simple, but you'll only remember the process, I believe, if you understand it. So I've got a square there. Now what happens if I if I have a similar shape, which means it's twice in both directions? How many times bigger is the area? So if we say that this is 1 square meter, how many square meters is our new shape? And I'm hoping you can see that we've doubled the lengths in both directions. So the lengths is times 2. The area is times 4, but I'm not going to write times 4 straight away. I'm going to write times 2 squared is times 4. Now imagine I was to take this on to make imagine this here was a cube, and instead of being times by 2, I'm going to do this by 3 because I think I've just got room to go times 3, so that would be to about there, wouldn't it? And that would come down that bit further to be like that. Now if I continue dotting that all the way across, I'm hoping that you can see that when the length is times 3, the area, this looks a bit like the face of a Rubik's cube, doesn't it? The area is 3 times 3 is 9 times. And the impact this has is if you've got an object, the surface area of it will be 9 times what it is, because every face, it's got 6 faces, a cube, hasn't it? Every face is going to be 9 times as big as the one before. And then you could take that into any kind of weird shape you like. It'll be 9 times. Now, I also want you to consider similar shapes, volume principles, because if we were to continue, let's do this one first of all, continue this on, maybe let's go for a different colour going straight down. That might make it clearer. If I was to continue down, that's timesing it by 2. That's timesing it by 3. And then it's about the same there. And if I was to continue doing that, so that my cube is now 3 times the size in length, so the dimensions are 3 times the size, but the volume is going to be many more times that. You're going to have 9 cubes just at the top. Imagine these were glass cubes. You'd have 9 of them just at the top that I'm drawing in just there. That's getting complicated, isn't it? And then you're going to have 3 rows of those 9s going down below. I won't draw all of that in. So the point is, the volume is going to be the length that it's increased, which we call the scale factor cubed. So scale factor 3 is another way of doing it. So the scale factor tells you how many times the dimensions have increased, so that will work for the lengths, comparing the lengths of any similar 3D shapes. The scale factor squared will tell you how many times bigger or smaller the surface area of a similar shape is, and the scale factor cubed will tell you how many times bigger or smaller the volume, the amount of 3D space you get out of a 3D object is. And just to finish off, as far as the times 2 one's concerned, the volume will be times 2 cubed, and 2 cubed is 8. So if we had it going times by 2 in each direction, that would be like that, wouldn't it? And hopefully you can see that we're going to have 8 cubes, 4 red cubes on the top and 4 underneath. Right, so there's a bit of the logic behind it. Now let's get the worksheet out that you should find, that you can download. If you can, print it off. If not, just make notes. It'll be just as good, especially if you like a bit of art and enjoy sketching. Here's our first question, so take your time. Underline the important information or write down the important information if you haven't got it there, and go from that. Right, so we've got 2 solid shapes, A and B. They're mathematically similar, so that means that we will have a scale factor, and the first thing is to find that scale factor. The radius is 4 centimeters for shape A, is 8 centimeters for shape B. So what I'm thinking is, how many 4s make 8? What's the multiplier from the small shape to the big shape? And that means that I can say the scale factor is 2. And if the scale factor is 2, I can say that lengths or dimensions for shape B are 2 times bigger. Area or surface area will be 2 squared, which is 4 times bigger, and volume will be 2 cubed or 8 times bigger. So if we are told the surface area of shape A, we don't need to worry about how you work out the name of this shape. It's called a frustum, by the way, in case you're interested. All we need to do is think, I'm going to do 80 times 2 squared, which is 4. And I mean, you don't have to write both those down, but I think it's a really good way to make sure you think through the problem, because a very common thing is that people write 80 times 2, and you could pick one markup at the beginning because you've found the scale factor, but that's it. So that's 320 centimeters squared. And then the second part of the question, if we pop down to here, is work out the volume of shape A if they tell us that the volume of shape B is 600 square cubic centimeters. So we're saying A times by 2 cubed equals B. So if we're going from B back, we're dividing by 2 cubed, which is 8, isn't it? So we're going to do 600 divided by 8. Now this would be probably in a non-calculator paper. If it's numbers like this, it'd be nasty numbers, it would be in the calculator. 8 into 6 doesn't go. 8 into 60 goes 7 8s are 56, remainder 4, 5 8s are 40, so it is 75 cubic centimeters, and we can pop that on the line, dotted line there. And that's that one. So on to question 2 next. Question 2, pause the video and give it a go. So the key thing, first of all, is to find out what the scale factor is. There's no dimensions put on there, but it says that the height of cylinder B is twice the height of cylinder A. So if you're timesing by 2 to make something, that means the scale factor is 2. So that may help if you need to pause the video again at any time. If I say something critical and you think, I think I can do it now, pause it and keep going, and then see if you're right. Total surface area is 180 centimeters squared. Calculate the total surface area of cylinder B. Well, length will be 2 times A. Area will be 2 squared, and volume will be 2 cubed. So what do we want? We want area 2 squared, the total surface area. Doesn't matter that it's a 3D shape because of everything that we did. If you're getting confused, go back and watch my demonstration with the cubes at the beginning. It doesn't matter what the shape is, that's what's going to happen. So if we had 180, we're going to do 180 times 2 squared, which is 180 times 4. Double 180 is 360, times it by 4 is 720 centimeters squared. And that's all that is. A pretty straightforward 3 marks really, but so often people just do times 2. They get 1. They get 1 if they're lucky, to be honest. Sometimes it doesn't happen at all. Depends on the mark scheme. Right, so question 3. Here's a far more confusing looking question. And we are going to have to do some working out of stuff and using the formulae. But I say using because they do give you the formula. And that is what it's going to be like in the GCSE. It won't be on the front of it, but they occasionally, you get these ones like this. You don't need to remember this formula. It'll be there, but you do need to think about how you use it. So pause the video and have a go. Right, now working out how to do the volume of this, that is it, but it's not that difficult. All we need to do is we need to work out the volume of the whole cone, and then we also need the volume of the small cone. Take away the volume of the small cone from the volume of the large cone, and we've got frustum B. Okay, so the frustum is that little bit, that bit there. So the large cone, if we do that, it says it wants it in terms of pi, so this is going to be a non-calculator paper. So large cone, and it says the volume of a cone is going to, and they've told us about the surface area. I don't know why they've done that, because this question's only asking for the volume. Maybe so that we can be sure that we don't need it, because the volume is from here. So the large cone is going to be 1/3 pi times the radius. So the radius of the large cone is going to be half the 18 there is 9. So times 9 squared. And the height of the large cone is 4 plus 2, making 6. Then we're also going to need the small cone. So if we call that cone A, we'll have 1/3 pi again, multiplied by the radius this time is half of 6, which is 3 squared. And that's going to be multiplied by the height, which is 2. Now we could do this by working out that one and then using similar shapes, but we don't need to, so I'm not going to bother. And you might have done that. If you did that and get to the same answer, then don't worry, just wait for me to gabble on and finish. So I could do, right, so I'm just going to write 1/3 pi again times 81 times 6, and then I'm going to consider the fact that 1/3, when you could cancel 1/3 with 6 and get 2, so 2 times 81 is 162, so we've got 162 pi for the large cone. Now for the small cone, 3 squared is 9, so we've got 1/3 pi times 9 times 2. 1/3 of 9 is 3, so 3 times 2 is 6. That's giving us just 6 pi. So the volume of the large cone is 162 pi. The volume of the small cone is 6 pi. 162 take 6 gives us 156 pi centimeters cubed. Now that is down there at the bottom on the bit that you should really write it on, but I'm just going to leave it there. And that's all I've got time for today. I would really like you, please, to have a crack at number 4 and upload that to me, and I'll go through that at the beginning of next time before we cover the rest of the questions in this, because it's really worth practicing and they do get a little trickier. Okay folks, take care, see you next time.